approaches and what its advantages are. And primarily there's three things we're going to be handling with these models, and that's the flow distribution modeling, the heat transfer process modeling, and the combustion process modeling. So the great thing about Flownex simulation environment, which is the tool that we're using to create these 1D network models, is that we can incorporate and combine all three of these aspects within the same environment. So once I've discussed that, I'll briefly go over a Flownex benchmark and demonstration model, and you guys will get a hands-on look at the user interface and the tool and how one can interact with it. So again, just to summarize some of the reasons for 1D flow network tool, during the preliminary design phase, or when considering modifications to existing designs, it's essential to make realistic predictions of mass flow splits through various air admission holes in the combustor. It's critical to be able to predict and determine total pressure losses, and then also determine what liner temperatures are along the length of the combustor as well. So although this is possible to do with full 3D CFD, CFD solutions are specialized, time-consuming processes, and therefore seldom used during the initial sizing of a combustor. And that's where kind of Flownex really fits in. It's a network tool, which means it allows accurate initial designs. It means you spend less time on advanced 3D simulations and building test rigs, and ultimately you just reduce development time and cost. So what is the 1D network model approach? So you can think of it as a set of independent subflows linked together to model certain processes. This can be achieved by overlaying a network on the system geometry, so basically defining the geometry in terms of a 1D model, and this typically comprises of elements that are linked together with nodes. And between those nodal points, you are conserving mass, momentum, and energy, basically just solving the conservation equations. And what this means is that these network models are capable of modeling both incompressible and compressible flow, and like I mentioned, it allows the integrated prediction of flow distribution, combustion, and the heat transfer processes as well. So what that ultimately means is that we're able to determine and account for parameters such as gas temperatures, combustion efficiencies, gas emissivities, and then we can also incorporate correlations to predict foam cooling efficiencies. And these are typically obtained from empirical formulations, and I'll be discussing those a bit more in detail later on in the presentation. So what are the advantages of this approach? What it allows us to do is model complicated geometries without too much difficulty while maintaining speed. So these networks solve pretty quickly, in the order of seconds. And that means we can look at several design modifications pretty quickly as well. So we can parameterize values, run parametric studies, and kind of take a look at how varying parameters can change the response of our network or our system. I'll be covering in the example I'll be going over. You'll get a first-hand look at how we can set up parameter tables within Flownex to vary things like engine operating conditions or even engine geometry. So one other advantage as well of having a 1D network model is that you can use results from that model as boundary conditions to a 3D numerical model as well. So if you have determined heat transfer coefficients and bulk temperatures in Flownex, you can use those as boundary conditions to, say, a thermal analysis, thermal FEA analysis. If we look at flow distribution modeling, basically, this aspect of it just allows us to predict the distribution of flow and mass flow rates through the gas turbine combustor. So elements such as restrictions and ducting components can be used to define actual geometric features within your model. And again, we employ several empirical correlations or semi-empirical correlations to determine what the pressure drop relationships are, in each component or each area in our model. With regards to combustion modeling, you can imagine that the combustion process is pretty important and has to be accounted for because gas temperatures affect fluid density and therefore flow distribution and pressure loss results as well. And then also you need to have an accurate gas temperature profile within your combustor to predict wall temperatures. So how Flownex handles the combustion modeling process is by linking to a NASA CEA program. This is kind of all happens in the background. User isn't really aware of that, and it's not very difficult to set up, but what it's essentially doing is based on air-fuel ratio and the fuel composition. It's calculating what the adiabatic flame temperature is and also the composition of your off gases as well. So the next section, I'm just going to go over some of the empirical heat transfer correlations that have been implemented in Flownex. For the most part, prediction of liner walls temperatures is achieved by conducting a heat balance along the liner wall. Typically, the inner wall is heated by convection and radiation from hot combustion gases and cooled on the outside by annulus airflow through convection and radiation from the outer liner surface to the casing wall. This requires specialized cooling mechanisms be employed, mechanisms such as convection, filament, jet impingement cooling, fluid and surface to surface radiation, and conduction as well. So while Flownex has several heat transfer correlations implemented within the tool, it's important to realize as well that it's possible for users to incorporate their own custom correlations into the tool pretty easily as well. So any user-defined function, whether that be a correlation or a custom pressure drop, that can be implemented through some scripting by the user. So just going into a little more detail with regards to each of these heat transfer mechanisms. If we look at internal radiation, typically this is a major contributor of heat transfer from the hot gases to the liner wall. If we look at external radiation, this is heat transferred from liner to the casing. It's usually small compared to the external and convective heat transfer, and it's approximated by assuming gray surfaces with known emissivities and view factors. So heat transfer process modeling in terms of convection and conduction. Convection, we typically just assume that a classical heat transfer correlation for straight pipe, something like Dietz-Bolte, will hold for conduction inside the liner. And for external convection, the Reynolds number is typically based on a hydraulic mean diameter for the annular airspace. So in that annulus around the combustor itself, we just apply some hydraulic mean diameter to that standard Dietz-Bolte correlation. If we're looking at conduction, it's pretty straightforward, and we refer to Flownex as a one-dimensional 1D tool, but if we are talking about heat transfer, we can typically model that two-dimensionally because we not only model conduction, but we also model cross-conduction between components as well. So with regards to foam cooling, so foam cooling represents air injected through the slots, through slots or holes axially along the inner liner wall, and this provides a protective film of cooling between the air and between the wall and hot combustion gases. So again, there are a couple of standard correlations implemented within Flownex. The user can pick from these, take things like blowing ratio into account, hole size, distance from hole, everything you would expect. Impingement cooling. So impingement jets typically provide an effective mechanism for heat transfer as well, and can be positioned to provide extra cooling on liner hotspots. There's this one or two correlations for that implemented within Flownex. Again, those are pretty standard correlations for the gas turbine industry. So just to discuss the benchmark itself. So we went and implemented this all in Flownex, and we had some customers in industry using it, but really to prove our capability, it was necessary for us to benchmark our results against published non-proprietary data, and what we were able to source was a NASA-funded data from a NASA-funded energy-efficient engine program. So it's an interesting geometry. It's a double annular combustion liner. I'm sure some of you might recognize it, but myself and one of the developers at Flownex actually co-authored a paper, and our efforts are documented, and you guys can go and look that up, or if anyone's interested in reading the paper, please reach out to us and I can send it to you. But I'll be going over some of the results in our approach in the next couple of slides. So basically what we ultimately ended up doing was just creating a complete conjugate flow and heat transfer model of that E cubed or E3 combustor, and we can look at it just to kind of give you a closer look at what it looks like just at one of these cooling slots. We can see we have several, let me highlight right here. We have several components here that represent the conduction through the liner wall. We have these elements right here that represent convection on the cold side, and then these components down here represent film cooling on the liner hot side, and then also radiation from the main flow path. So for the benchmark, we had several operating conditions from that paper that we used as boundary conditions to the network model, and these were pretty easy to parameterize in Flownex. So we had several different test points, different inlet pressures, temperatures, combustor flow rates, fuel ratios. So we had several test cases we could compare Flownex results to the actual test data itself. With regards to the airflow distribution, it was kind of hard. The paper was published several years ago, maybe in the 70s or 80s. I can't exactly remember, but it was kind of hard for us to back engineer exactly what the geometry for the test rig was. But what so we didn't really know exactly what the exact geometry of the air admission holes were, but what we did know was what the overall airflow distribution through the combustor looked like. And Flownex has a designer tool in it, which allowed us to essentially specify what mass flow rates we wanted through each of those holes, and back calculate the hole size, which was pretty neat. If we look at metal temperature results, so we're just looking at 3 of the liner panels right here, and each of these points just corresponds to a point on the liner wall. So you can see kind of how many times we've discretized each of the panels, and this point right here is right around there, so it's right at the slot exit. And you can see as we move away from the slot exit or the source of the film, we have an increase in liner metal temperature. This is a trend we see repeated for each of the panels. So as that film effectiveness or foam efficiency drops, our liner wall temperature increases. We see an interesting little phenomenon here where our, our, our temperature drops off a little bit, and that's just due to cross conduction from the downstream slot. So that's kind of what our metal temperature results looked, and each one of these lines represents different one of the test cases I showed you before. But what we also actually had was temperatures measured at 2 points or 2 locations where there were thermocouples on the test rig, and we compared Flownex to those Flownex temperature results to those 2 locations as well, and overall the simulation results showed good agreement with the test data. The percentage errors in liner wall temperatures ranged between 1 and 13%, which was really fantastic. So before I get to the actual Flownex demo model itself, I just want to show you guys. I just want to again highlight why Flownex was a great tool and why we decided to use that for this specific application. So again, it's a commercial 1D thermal fluid network tool that employs conservation of governing equations. And I say commercial there because there's a lot tied up in that word. So what we encounter a lot is that large aerospace companies typically have been historically using in-house codes to model this type of model to solve these types of problems. But with that, you typically have to be doing maintenance on a tool. You typically have to be in support on a tool and verification, validation. With a commercial tool, the benefit is that all of that is handled. Is not really your problem anymore, right? On top of the fact that Flownex is modern, it has a really user-friendly interface. Most in-house tools don't have very friendly interfaces, and they're kind of dated in that regard. If we look at some of the other reasons why we use Flownex, again, the fact that we have that integrated CEA calculation or chemical equilibrium calculation is super helpful. There is a large library of industry standard correlations for gas turbine heat transfer already within the tool. That being said, we recognize that many companies have been developing their own correlations for many years, and for that reason, we make it pretty easy or flexible and possible for people to script in their own correlations or user-defined functions. Flownex solve time is really quick. It's easy to set up sensitivity analysis. And something I don't really touch on in this presentation is the fact that we can easily map or link or build hooks into a third-party FEA, CFD, or other post-processing softwares. So we've done this in the past with ANSYS, but that's not to say we can't do it with any other FEA or CFD products.
Stephen, sorry to interrupt you for a second. We've got a question from Reddy Butler. Would you like to just speak to Stephen for a second?
Paul. I can't hear anything. If you just want to type it into the chat, you can do that too.
Okay, maybe we can get back to that in a second. Yeah, if you can please just type your question into the chat, then we'll answer it as soon as there's a pause in the question.
Okay, if you guys can see this model, what you're looking at is essentially just a JPEG or a PNG. It's just a standard image file format that we're able to incorporate into the background here, and we're able to construct our network over it. So this is just a CAD model that we recreated based off of some drawings in the NASA report, and then we just proceeded to construct a Flownex network using several of the heat transfer components in the database, or sorry, in the library. You can see things like film convection, fluid radiation, jet impingement convection, surface radiation. So depending on the area of the model and the mechanism of heat transfer we're expected to see there, we're able to select a component, drop it down on the drawing canvas, and in that way, reconstruct or create the network you're seeing right here. So again, if we look at an individual panel right here, we have air coming from what is a duct section here that represents the annular flow path. So it's coming into this slot, it's cooling this air. We have some dilution holes as well. They don't really affect the heat transfer right here. And then we can proceed to specify geometric inputs to each of the components in the input window here on the left. So as you can see, it's pretty neat, pretty clean interface, extremely user friendly. The learning curve is not very long. Anyone who's played around with it a couple of hours can start constructing some sort of basic network within the tool. If we look at the actual combustion process, we have this combustion element, and again, it's just based off of what my inlet air and fuel composition is. I can go look at this downstream element right here. It'll calculate the mass fractions of the resulting from the combustion process, and also a flame temperature, which I can use as a reference temperature for my radiation calculations, for my film convective calculations, and so on. So we then transfer heat from this main gas flow path right here all the way up to our liner walls. So just touching on some of the ease of use aspects, within Flownex there are a whole bunch of ways that we integrate with Microsoft Excel. So that's in the form of results overviews, or sorry, result spreadsheets. So I can pretty easily generate a result report, link certain cells in an Excel spreadsheet to result parameters from my network. And that's basically what I've done right here, and I'll show you that in action in a few seconds. But what's also neat is this parameter table. So what we're looking at is for different cases, so 10, 20 to 10 to 60% operation, I have different inlet pressures, inlet temperatures, fuel flow rates, and so on. And what I can have Flownex do is run through each of these cases sequentially. So I'll go ahead and run that sensitivity analysis, and if I go back over to my temperature results, what I'll see it do is repopulate this Excel file with new result data. So as it's stepping through each of these iterations, we'll see how we're lining up with that orange line, this test data, and that blue line is a Flownex result. Right now it's in that case, and it's moving on to this one right here. So again, these reports are completely custom, and they're really easy to set up. It's all just drag and drop. So let's say, for example, I want I want to know what a temperature result is, let's say at that point on my liner, and I want that to be in my result report. I can just go and drag that temperature result and assign it to a specific node. So there it is right now, and now it's kind of hot linked. So every time I rerun my simulation, what's going to happen is it's going to repopulate that cell with the new value. I just I've discussed solver speed quite a lot, so I just want to showcase that to you. So this is a pretty large model. I wouldn't say it's very large, but there's maybe a couple of hundred nodes and elements in here. And if I solve that guy, I can see that I converge fully within 2.3 seconds. So pretty quick. And for that reason, you can run through hundreds of different cases and kind of look at how different parameters affect your results. Yeah, that's pretty much all I had to show you guys today. Again, there'll be a few minutes now for questions. If any of you guys want to unmute yourselves or type into the chat, we'll hang around. If not, if you guys want to pop or send either myself or Vince an email or would like any of the information that we discussed today, I can share that paper that we published as well. Please feel free to reach out.
Stephen, we do have two questions. Pravin Akod would like to know for the combustion calculation, he's just asked inside the chat, in the combustion model, is it an equilibrium calculation? He refers to global chemistry. If you'd like, I can unmute you very quickly and you can discuss this with Stephen. Just Pravin.
Hi, Pravin. So I can't see your question, but just to stress again what this is doing, it's just a chemical equilibrium calculation. So if we look at this this inlet right here, so I specify my fuel, and then I have some air coming in through this restriction that represents sort of the air inlet or the injector perhaps. So it's doing that equilibrium calculation, and it's then just calculating the results. But that being said, there are several of this is one way we've approached the problem. But if there is any any other method that you would want to incorporate into the tool, that would probably be pretty easy to do. Whether you're running some external executable or some external script, or you incorporating that calculation within a script in Flownex, that's possible as well. There's also ways to represent combustion just characterized in terms of a table. So for different fuel air ratios, you can have a different resulting flame temperature, and you could simplify the problem that much if that's what you wanted to do as well.
Okay, I think that answers my question. Thanks, Stephen.
No problem.
Stephen, we have just one more question. It is from Gokhan. He asks, basically, does Flownex have the ability to calculate emissions?
I'm not sure what you mean by emissions. All it really does here is just calculate the resulting gases from the combustion process. So what you typically need to do is so you specify your fuel and your air, and what you also need to include in the fluid configuration definition is all the off gases that you would expect in there, right? So we know that there's going to be some water vapor resulting. We know there's going to be some nitrogen, some hydrogen. And what Flownex will calculate is what the mass fractions of each of those resulting gases are. Does that answer your question?
Okay, and your mic is unmuted. If you'd like to speak, just click the unmute button. Otherwise, just feel free to respond to the question. I think that's it. Then just one last question from already. He typed his question in the chat. He asks how to to actually make the coupling between Flownex and CFD, say Fluent. I've got a video that I can share, but maybe Stephen, you can just talk 2 seconds on it.
Yeah, we can provide some information afterwards, but if we look here in our library, we have a mechanical and a Fluent link already kind of built in here. So with regards to Fluent, there's both a journal coupling and a server coupling. So how the journal file coupling works is, so if you're familiar with Fluent, a journal file basically is just a script which dictates order of execution. So you can say you can initialize values. So you can initialize your solution. You can specify how many iterations it needs to run. You can specify certain values as well. So what this component actually does is you specify the location of a journal file, and it actually just modifies parameters in that journal file based off of Flownex results. So Flownex will read the journal file, it will change a parameter, it will update a parameter with the Flownex result, and then it will run ANSYS, retrieve a result value, and then rerun. The solver coupling is a little more sophisticated than that, but basically how it works is you have some sort of flow resistive element in your Flownex model that represents the component in ANSYS, and based off of what our pressure loss is and our flow characteristics are in Fluent, we then go and change the flow resistive element within Flownex, and it's sort of like a back and forth, a co-simulation in that way. Again, these components drive the process completely. So they'll launch Fluent, they'll run it in server mode, they'll pull values back and forth. That's basically the premise, but we can certainly send you a video, and I believe there are a couple of examples. If you have access to Flownex already and you go to the start page, there'll be a whole bunch of demo networks and video tutorials, and I'm pretty sure there's one on the Fluent server coupling in here somewhere as well, if you want to use that as a starting point to sort of link your own models.
Yeah, Stephen, you'll find it at the bottom of the demos list. Anyways, just some additional information. If you look in the chat, I've pasted a link to a YouTube video. It's a video posted by our British reseller by the name of Wild. They did an integration between a 1D Flownex simulation and a 3D ANSYS simulation. So it just covers a small presentation discussing the uses of it, and then some of the applications, and then it shows a particular example where a co-simulation event has been done inside Flownex. So if you would like, you can take a look at that. All right. Stephen, just to follow on to that last question, Gökhan just asked, can only premix or non-premix models solve? This is related to the combustion again. So,
no. I think we can handle both. So if you're referring to the fuel premixing with the air, then yeah, it's not a problem.
And then jumping back to another question from Paul Reddy, he says, how to modify the location of film holes on the surface of the combustor?
Film holes on the surface of the combustor. Okay, so let's look at this example right here. So basically, how we represent a distance away from a film slot, from a film hole. So say this is a film hole. Excuse me, let me just mute that real quick. So let's say this is a hole right here, and this is one right here. So the distance of each of these increments, you could look at them away from that slot, is just an input parameter to our film cooling component. So we give that specific section a x1 and an x2 value. So we can see for this first guy, it is 0.3 inches away from the hole. The second guy is 0.3 to 0.6 away from the hole, and that's kind of how we break it down. So we did this, we split this up just to kind of see how grid dependent the model was, but you could, for argument's sake, just have one of these components representing each film slot, and then when you're setting up your parameter table, you would just have these x1 and x2 parameters be varying, and you could run a whole bunch of cases investigating what the distance from the distance away from the spacing between the slot holes had on a line of wall temperature. I hope that answers your question.
Thank you, Stephen. Are there any more questions? I don't see anything more in the question section or in the chat at the moment. Okay, perfect. Thank you very much, Stephen. If you are interested at all, please feel free to contact us. You should receive an email after this webinar as well. This recording will also be placed on our website, so you can refer back to that as well. But if you do have any questions, feel free to contact us. Myself and Stephen's email addresses are both available inside of this GoToMeeting interface. Stephen's email address is stephen.taron@padinc.com, and mine is vincent.brits@flownex.com. The spelling of these you can both find inside of the interface. And yes, thank you very much for attending. I hope you enjoyed the webinar. Thank you very much, Stephen, for your time. And yes.
Thanks, Vince. Thanks, guys. Have a good day.